Broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and thank you for joining. This is actually the sixth webinar series of 2021 of the Metabolomics of the Early Careers members of the Metabolomic Society. My name is Evelina Charidimou, and I am based at the Department of Biological Sciences at the University of Cyprus. And I will be co-hosting this webinar with Alvaro from Max Delplague Center for Molecular Medicine in Germany. So I would like to inform you that all the material will be recorded and it will be uploaded to the Metabolomic Society website. So you can have access to this live content at your own convenience. And I will give this stand to Alvaro now.
So hi everyone, thanks for joining us again. So we encourage you to connect with us online social media networks via Facebook or Twitter for future content. And feel free to email us with any suggestion for future speaker or topics for next webinar or other input.
So we're delighted to host this webinar today with Dr. Boccard, who is a senior research associate within the Pharmaceutical Analytical Chemistry Group at the School of Pharmaceutical Sciences of the University of Geneva. His research interests are focused on data mining strategies applied to life sciences, including chemometrics, machine learning, and bioinformatics. He is also an elected member of the administrative board of the Francophone Metabolomics and Fluxomics Network since 2015, and he's also a member of the committee of the Swiss Metabolomic Society since 2017. Along with Dr. Boccard is Dr. Miguel Figueiredo, excuse my pronunciation, who's a postdoctoral fellow within the Pharmaceutical Analytical Chemistry Group as well at the School of Pharmaceutical Sciences of the University of Geneva. And he's focusing on developing innovative chemometrics and bioinformatics tools for the longitudinal profiling of endogenous steroids for the detection of doping. So now I will give this stand. I will also pass you to Alvaro before we give this stand to Dr. Julien.
So before today's talk, we would like to announce our first webinar for next year. This will be on January 19th and will be given by Peter Dorestein and Dr. Emily Gentry. This webinar will be about metabolite annotation strategies in untargeted metabolomics and discovery of new metabolites, including microbiome-derived metabolites. And more details will be posted very soon in the Metabolomic Society website and our social media networks. And for today's talk, please remember to submit your question throughout the presentation in order to be answered in the Q&A session part at the end of the webinar. Please indicate the speaker name in any of the questions to be addressed to them. Yeah, so I will thanks again to both the speakers for today, and now is the turn to Dr. Julien Boccard. So thanks again for being our speakers today. The stage is yours.
Thank you. Hello, everyone. Do you see my screen? I hope it's the case.
Yes, we can see the screen.
Okay, perfect. So thank you for this kind introduction, and thanks to the EMN for the invitation to give this webinar. As you can see, we are going to talk about data analysis today. But before diving into the world of data structures, I just would like to briefly present our research group in Geneva. So Miguel and I are members of the team of Bioanalytical and Metabolomics Analysis, which is headed by Serge Ruda, the School of Pharmaceutical Sciences of the University of Geneva. And we are, in fact, part of the Analytical Sciences group, which involves also our colleagues who are working on fundamental aspects of separation techniques, such as liquid chromatography, supercritical fluid chromatography, for the analysis of small molecules but also larger compounds. So what I wanted to stress is that it's very interesting for us because we can benefit from their analytical expertise and skills to develop our workflows that we apply to more specific biological questions. And it's really a great chance to work as a team with them. And I will also like to take the opportunity to mention the two scientific societies in which I am involved, and that are actually official affiliates of the Metabolomic Society. First, the RFMF, which in French stands for the French-speaking Metabolomics and Fluxomics Network. It is a very dynamic group of researchers coming from France, of course, but also Belgium and Switzerland. And I also wanted to mention that we have a very active junior section, which will organize a European School of Metabolomics in March 2022. You can see the address of the website on the slide, so don't hesitate to visit this website if you're interested to learn more about this event. And I'm also a member of the board of the Swiss Metabolomic Society, which gathers people from academia and industry. And even if Switzerland is a small country, we have the chance to benefit from a high density of institutions and biotech companies. Well, of course, we are still a small society, but we try to promote metabolomics in Switzerland and through scientific events, webinars too, and other activities. So again, feel free to visit our website if you are interested in our activities. Okay, so let's talk about data analysis in metabolomics now. And this has actually become an important subject today because our ability to generate data has actually completely changed. Because today, modern technologies allow us to record, to generate massive amounts of data to describe a phenomenon using experimental data. And this has changed a bit the way we can imagine our research project, because the classical way to do things is actually a kind of hypothesis-driven approach in which you will of course read the literature and then start to build hypotheses that you will try to check in a very specific manner. You will bring experimental proof for very specific questions. So this can be seen, if we can say, as a kind of reduction strategy, because today, because of our ability to collect data, we can move to a more holistic strategy, and we try to have maybe less hypotheses at the very beginning of the study. We collect data, and starting from those data, we start to build hypotheses that can explain the phenomenon we are looking at. So this ability to generate data has a bit changed the way research can be done today, and this is, of course, specifically the case in metabolomics. So now the question is how to make sense of the mass of data we are able to collect today with very performant MS devices, NMR apparatus, and others. Most of you probably know well this knowledge discovery workflow in metabolomics. And of course, it starts with data acquisition, and then there is a need for skills in analytics at the very beginning of the acquisition process. Then we move to the processing of those data, and again, we need to know what are the intrinsic characteristics of our data to extract the part of the signal that is relevant to explain the phenomenon we're looking at. There are different steps of normalization, of annotation, and then comes maybe the part we are mostly involved in, Miguel and I, which is maybe more centered on data mining and chemometrics, because as you will see, because we're able to generate a large amount of data, we need adapted tools to extract what is actually the real information within the mass of signals we have been generating. So this includes, of course, data analysis approaches for the exploration of the data, if you have different classes to make the distinction between the different groups of your experiments. And at the very end, of course, we are mainly interested in patterns of signals of variables that can be related to specific biological situation. And this is the end of the workflow. It's to put the statistical results into a biological context. And this is mainly the role of bioinformatics there. So to describe a bit in more details, the tools we're developing for this chemometric part of the workflow, we have been discussing the fact that we can actually divide our data set in 4 main categories. And as you can see, the first one is the fact that we have to deal with very, very large data matrices with usually a limited number of observations, but a huge number of variables. And this is the question of dealing with high dimension matrices. And you probably know multivariate approaches to deal with that, such as principal component analysis and then other approaches. But this is maybe the simplest situation because we only have a lot of variables. Today, more and more data are generated using experimental design. And in that case, you will start to adjust parameters simultaneously to assess their effects on the metabolomic profiles you're measuring. So this adds an additional complexity to the dataset, and I will discuss also about that in a few minutes. Another structure that we see quite often is the fact that we are following observations and we measure variables, but sometimes there is a third dimension that can be also measured in the data. For example, if you follow a phenomenon over time, this will intrinsically generate this third temporal dimension, and you will see that there are dedicated tools that are very helpful to handle this kind of data structure. And finally, I would also like to discuss about this kind of setting where multiple data matrices are used to describe the same series of observations. And this is called multi-block data analysis. And you will see there that there are also solutions to analyze this kind of data sets. So let's start maybe with the first case, which is the high dimension data matrix. And today I will mostly talk about multivariate data, but actually the multivariate data are known for a long time because it only needs to have several variables to describe a series of observations. But in the classical setting, when classical multivariate tools can be applied, we need to have more observations than variables, and those variables need to be not too correlated and almost noise-free. So of course, if we have to deal with metabolomic data, we are completely the characteristics are completely different because most of the time we have a limited number of observations, but a very large number of correlated and often noisy variables. So all that to say that actually classical regression tools cannot be applied anymore to metabolomic data, and we have to find new solutions to extract what is the meaningful information within the data matrices. There we can see two aspects to extract this information from these large data matrices. The first one is called feature feature extraction, that will aim at summarizing the whole data matrix using a limited number of new dimensions, and this is usually done with projection methods. Again, you probably know principal component analysis and other extensions of this classical multivariate method. So this is one way to do things, trying to summarize the complexity of the data matrix using a new set of synthetic axes. And the other possibility is to select what are actually the meaningful variable, the meaningful signals that could be used to explain the situation you're looking at, for example, to distinguish your experimental groups. And this can also be seen as a selection of the variables that are important to differentiate, to discriminate your experimental groups. And this can be done using selection algorithms. All that to say that I will mainly talk about multivariate models today, but it's perfectly fine to apply univariate approaches. You can perfectly evaluate the individual merit of any variable for the comparison of your two groups, for example. So you can rely on maybe more classical tools that can be either related to statistical tests or, well, of course, in the case of a large number of variables, you will have to correct for this multiplicity of tests. But again, you can use classical tools to analyze the individual value of all the variables. Another important aspect, I will not go into details today, is the fact that, of course, you can evaluate individually the importance of the variables, but most of the time, building subsets of features is very often more useful to describe a phenomenon in metabolomics. And this selection is, again, a whole topic in itself, so I will not go into details, but keep in mind that this selection, of course, can be done using complex algorithms that will try to improve the prediction performance based on complex approaches. But you can also apply the prior knowledge of the system you're looking at, the prior knowledge about the phenomenon you're looking at, and use the annotation. That can be also a very efficient way to get rid of signals that are actually not useful to describe your experimental data, and focus only on the signals you are able to associate with a biological compound. So variable screening and filtering can be done in many different ways. And again, this is also perfectly fine to work with a subset of variables to explain a situation. But again, there is also another possibility to try to summarize the data set in an effective way. And this is done using dimensionality reduction approaches. Because one very important problem we have to face when we try to analyze these large data matrices is that the fact to add additional variables to the matrix makes that the hypothesis space to look for patterns that explain the phenomenon you're looking at become really harder to find in this huge space of hypotheses. And in that case, it can be very efficient to try to summarize the signals you were measuring using a mathematical model. And this model will aim at the extraction of information that is not directly observed in the data, but this is called latent information. So the mathematical model will make the bridge between the observed signals and the phenomenon you're trying to describe. Then the question is, of course, which mathematical model to use if we want to be efficiently extracting this information. Well, so one of our answers to that is that it depends actually on the data structure. But in most of the case, you will try to build a subspace, and this will help you to display your observations, even if you have hundreds or thousands of signals. And as you can see on this slide on the right, you can have, depending on the mathematical criterion you use to summarize the data, you can obtain very different pictures of your data set. Here, if we rely on data variability, as it is the case for principal component analysis, you can see that even if the data set composed of those two variables here with blue squares and red dots, if we try to show the variability, the two populations will be completely superimposed. So if your aim is to distinguish the two groups, it will not answer your question. But on the other hand, if you take advantage of the experimental design and build a mathematical criterion that try to separate the two groups, you can end up with a very nice separation of your two groups, as it can be the case with this kind of discriminant analysis approach. I also want to stress on this slide the fact that we mainly rely on linear models because it's very important in metabolomics to be able to go back to the contributions of the different variables, because actually most of the time when you build a model in metabolomics, you already know that you have controls and you have treated observation. I mean, that the aim is not to predict the fact that a new sample will be controlled or exposed. So most of the time, the real added value of the multivariate model is more on the measuring the importance of the variables, ranking the variables according to their predictive merit, rather than the prediction of a new observation. So all that to say that our multivariate model will serve as a basis to rank the variables and to highlight subsets of promising or relevant biomarkers. So this was for maybe the simplest situation. Now let's move to the situation when we are trying to modify, to adjust different parameters simultaneously. This can be done when you're trying to evaluate the impact of the exposure to different doses, for example, to a given compound, and you want to evaluate whether controls, wild types, and mutants will behave the same with respect to this exposure and things like that. So of course it's very interesting to be able to assess those metabolic events and alterations by moving these different parameters simultaneously. So as you can see, those parameters can be of different natures. It can be quantitative if you want to use the amount of toxicants you expose your system. They can be qualitative with genotypes, for example, or ordinal if you add a low, an intermediate, and a high dose of something. And this is actually a very efficiently handled using experimental design. There is a whole theory behind this design of experiments that can be used to maximize the information you can get from your experiments. So on the one hand, you can have a lot of information about your parameters with doing only a limited number of experiments. This is one of the aim of experimental design. And on the other hand, if you perform what are called full factorial designs, it means that you try to assess all the combination of the levels of your factors, then you will have access to full information about the main effects of your factors and even the interactions between them. So it's very helpful to try to decipher what happens in complex biological systems. Then this theory is well known in the univariate case, as usual, but it starts to be quite complex when we have to deal with the high dimensional metabolomic profiles. So what happens with our data matrix? Here we have a matrix with a series of observations that are described by a series of variables. If we apply a first factor, then, for example, it will be helpful to distinguish the controls and the mutants in this first, with the two levels of this first factor. But if you add an exposure to a toxicant, for example, you have an additional factor that will have another impact on your on the data that are within your data matrix. Then you can add a third factor that will add an additional level of complexity. And at the end, it's very difficult, based only on the data matrix, to assess and to know which alteration is related with which effects. And so it's very helpful to apply dedicated approaches to be able to disentangle these different effects in the data. And again, this is well known in the univariate case. I'm sure you've heard about analysis of variance or ANOVA. That explains response here, a measured response based on an average value without any effects. And this value also depends on the main effect of factor alpha here, the main effect of another factor beta. So this is a two-factor equation. And here you have a term that is related to the potential interaction between these two factors. And of course, there is always the residuals, the error that is not related to the experimental factors. So in the univariate case, it's well known, and you can even quantify the amount of variability that is associated with each of these effects, with the total of variance that is decomposed into different sum of squares that are associated with the main effects of alpha, main effects of beta, the interaction, and the unexplained part. So it's very efficient to decompose the variability. It can even be extended to the multivariate case, but again, classical approach such as MANOVA, multiple ANOVA, is limited to cases with more observations than variables not too correlated and without noise. So again, it's not useful for metabolomic data as it is. In that context, actually, people try to develop approaches dedicated to the analysis of this data set generated using experimental design by combining ANOVA and projection methods, such as principal component analysis, for example. And the starting point is actually a similar decomposition of the data set. Here, this is our data matrix with observations and variables, which is decomposed into a series of submatrices, and then you can apply different projection methods to display the subgroups of the observations depending on the levels of the different factors. As you can see here, there are several approaches that deal with this question, and actually the main difference is related to the way those methods deal with these submatrices. But the starting point is more or less the same for all those methods. But I will not go again into too many details regarding these design of experiment approaches, because it will be the subject of Miguel's presentation. So let's move to the next structure, which is associated with this new dimension that can be obtained, for example, if you follow a phenomenon over time. And this is called a multi-way data. First, you have to know that some analytical devices intrinsically produce two-way data sets. So in that case, the starting point is a two-way array for each observation. And of course, if you collect a series of observation, then you get a data cube. Another case that is often met in metabolomics is the fact to follow phenomenon over time. So if we define a single observation at a single time point as a series of variables, then for multiple samples, we obtain the classical 2D matrix with different observation and different variables. And if you add additional time points, then you add this third dimension. And this is usually very informative to follow those metabolic phenomena over time. And of course, if you want to apply a multivariate model to this kind of data structure, maybe you will try to use your favorite software for that, and you will see that it's not possible to read a file from a data cube in any of the software you will use. So how can we manage this additional complexity in terms of structure? The first approach, very simple one, could be to break the structure, to analyze separately each of the slices, each time point, for example, and to have a look at the situation at T0, T plus 2 hours, 4 hours, 6 hours, and so on. Of course, at the end, you will have to analyze as many individual multivariate models you have as time points. And of course, you will break the links between the different observations that are actually followed over time. So if at some point you see that one observation has a specific behavior, you will not be able to relate this specific situation at this time point to another time point later on. And it could be very difficult to build a consensus analysis of all those multivariate models. Another way to simplify things could also be to average the slices and to get an overall situation over all the time points. But of course, in that case, you will completely lose the benefits that you would have get by following the phenomenon over time. So that's not maybe the best way to go on. Another approach that can be used with classical statistical software is to reorganize the structure and to unfold your data cube and to generate a 2D matrix that can be analyzed with classical tools. And you can see that with the data cube, you have two ways of unfold the slices. Either you will really worsen the dimensionality of the data set by adding the time points side by side and keeping the same number of observations. So you keep track of the same sample over time, but you completely disconnect the different time points. These variables are the same metabolites, but they are considered as completely independent variables. Of course, you will lose information there. And the other way to unfold the cube is this one, the vertical one, which is maybe more a better way to do it. But in that case, you will have the same number of variables, of metabolites, but all the observation at different time points will be considered as different individuals. So of course, first, it's not correct from a methodological point of view. And again, you will lose information about the behavior of a given individual over time. But the good news is that there are actually multivariate models that are designed to handle this kind of data structures. And those algorithms are called multi-way modeling approaches. And you can find similar methods as it is the case for 2D matrices with unsupervised approaches with Parafac and Tucker models, and supervised approaches with NTLS, which is an extension to a multi-way data structure of the classical partial least squares regression. And actually, this is not really completely different from what you already know from 2D matrix analysis, because you will have vectors that will define the observation, the variables, and the time points, in our case, in using new axes that will summarize the variability according to different criteria. You will have a latent value that will summarize the amount of variability that is summarized by each of the components. And you will end up with a series of plots, with score plots, that you will interpret as you would have done it with the 2D matrix analysis. And of course, in that case, it's much more interesting because you will keep track of the links between a variable that was measured for a given individual over different time points. To give you a small example, this is a study we've done in collaboration with the anti-doping lab in Lausanne, and they were interested in the metabolites that could be measured in urine after testosterone oral intake. So of course, for routine analysis, they have their biomarkers and they have their criteria, but they were interested to extend this panel of biomarkers by looking at some, let's call it the steroidomic approach, based on the untargeted LCMS data acquisition. And then we annotated the compounds based on the fact that they could be potential steroid metabolites. So we end up with profiles of 234 variables that were associated with steroid metabolites. The clinical study involved 17 volunteers that were divided into two groups, people taking placebo and people taking a pill of testosterone. And as you can see, there were 6 time points when the different urine samples were collected. The first thing we tried was to unfold the data cube vertically. So you can see that here we end up with a large number of samples that are actually linked to a given individual at a given time point. So it could be useful in terms of anti-doping for screening, because you can rely on a single urinary spot. But as you can see here, of course, you can see that some very different samples pop out of the cloud of the different sample population, and those are probably extreme of positive cases, because they are all on red. So it means that these are related to people who took testosterone, but we don't have any idea of what is actually the kinetic behavior of all the phenomena. So what we did then was to use the NPLS model to carry out discriminant analysis to try to separate our two groups with the placebo and the testosterone groups. And we were quite happy because the specificity of our classification was high, and this is of course needed for anti-doping control. And the sensitivity was much better than what they could do with their classical biomarkers. And as you can see, the interpretation of the model, of course, you have to validate your model as you would have done it for a 2D matrix analysis. But at the end, in terms of interpretation, you have plots, maps of scores and loadings you can interpret in the same way you would have done it in a classical 2D matrix. So with two components here, we were able to distinguish our two groups, placebo on the left and the testosterone on the right. And we were able, depending on the position of the different steroid metabolites on this loading plot, we were able to highlight which were the most interesting and promising biomarkers for anti-doping control. And this is what we could have also, we would have obtained by unfolding maybe the data cube horizontally, but here we have an additional information which is related to the third dimension, because we have score that define the observation, we have loading that define the variables, and we have another map that describes the kinetic behavior of the phenomenon. So here we just linked the different time points chronologically, and you can see that we were able, and we were happy to be able to highlight a kind of detection window that was quite different from the basal state at T0. And actually, we defined three states with the basal situation here, starting at T0, a kind of intermediate phase here, and a marked expression states at T2 and T3. It corresponds to 2 and 4 hours after the pill intake. So it's in accordance with the prior knowledge of this anti-doping study. And then we can see that the trajectory goes back to the basal situation at T4 and T5. So this was quite in line with prior knowledge of the kinetics and the elimination of this testosterone that was took orally with a pill. Okay, so that was for this multi-way data structure, and I would like to end with this last setup of data with multiple blocks of variables that are collected to define the same number, the same series of observation. And why is it so important today? Because I guess you all know that even if our analytical platforms are increasingly sensitive and able to characterize in a very impressive manner our biological samples, there is no single analytical platform that is able to cover the whole metabolome because of the complexity in terms of physicochemical parameters, of different concentration ranges, and so on. So a trend in metabolomics is also to try to combine different sources of information to get a more exhaustive picture of the samples you want to describe. And this leads to this collection of data blocks. And again, I would like to show you an example. This was a project in collaboration with a well-known flavor and fragrance company. And they were interested in the characterization of lemon essential oil because it's used in many different products that include the perfumes, cosmetic, pharmaceuticals, and foods. And they were interested, of course, to apply metabolomics to have a better idea of the quality of the products they use. There is also a question of authenticity behind this analysis, and they wanted to know whether the different samples could have been adulterated or not. So all that to say that they were interested to apply metabolomics to have a more complete picture of their lemon oil samples. So for that, they collected different samples all over the world. As you can see, samples were collected in Spain, in Italy, which are the countries in Europe that produce the largest amount of lemon oil, but also samples coming from Argentina. And you can see that there were also different suppliers in those countries. So they wanted to compare those different origins, including countries and different suppliers. And to increase a bit the complexity of their study, they also mentioned that actually the extraction process is very important to obtain a lemon essential oil with good qualities. And there are actually 4 main processes to extract the oil. The first one is called FMC. There's the sfumatrice process, and those 2 ones extract the oil simultaneously or after the juice. And there are also these 2 others with BOE and telatrice processes that extract the peel before extracting the juice. So, and again, this leads to different qualities in terms of essential oil. So we had 4 data tables to describe our 64 samples, sorry. We used GC coupled to mass spectrometry. We also use LC coupled to mass spec with 2 ionization with electrospray in negative and positive mode. And we also collected NMR spectra from all our samples. So the question now is how to manage this collection of data tables. And actually, the data fusion can be carried out at different levels. And you have here the different definitions of those levels. We can call high-level data fusion the fact to analyze separately the different data tables. You will then build a multivariate model with PCA, PLS, or all the methods you like for each of the blocks. And then from the outputs of the models, trying to build some kind of overall explanation of what happened in the samples. You will see that this can be useful, but it's somewhat limited, of course, in terms of interpretation. Then there is the mid-level data fusion approach. And in that case, the principle is to extract different variables, different features from each of the data tables, then concatenate those subsets, and then proceed to a classical multivariate analysis to get a model with scores, loadings, and so on. And maybe the most interesting one is it's called the low-level data fusion, where you, without selecting anything, you try to relate the different signals from the tables to build an overall model that accounts for all the data that is available to describe the observation. And again, you can apply those 3 kind of approaches with different goals, either to describe the variability in your data, to differentiate, discriminate your groups, or even to predict new observation. So we started with the high-level data analysis, and we applied OPLSDA just to see whether we were able to first distinguish the different countries. And you can see that it's actually the case with either either GC, LCMS in positive or negative mode, or NMR, the differences between the geographical origin is so massive, it's so important, and that it's quite easy to differentiate the samples according to their geographical origin. But of course, then you end up with multiple models, and you have to assess the contribution of the metabolites for all the different models. So it can be quite tricky to build a synthesis of all that. And maybe more importantly, we were not able to make the distinction between the different extraction processes, because probably the extraction process has a lower impact in terms of oil characteristics and compounds abundances than the geographical origin. So we had to do things a bit differently, to go a bit into more details to explain these potential differences. And so for that, we applied a multi-block data modeling approach. That is a low-level data fusion strategy, as I told you, that will account for the data of the different blocks together to build a kind of compromise model that will account for all the variables. And we can think about multi-block data analysis as a ecological motto, let's say, because we have to think globally to build, as I told you, a compromise of all the data blocks. But at a local situation, we have to act locally, because at some point we have to optimize some kind of mathematical criterion that will either try to separate the groups or try to explain the variability in the data. And all the game is to play at those two different levels, building a global compromise, but optimizing some specific criterion in all of the blocks. And again, of course, it's important using a linear model to be able to go back to the influence of the different blocks and the influence of the different variables. So in that project, we used an extension of OPLS, which is called consensus OPLS. I will not describe the details of this method, but just to let you know that starting from a series of data matrices, it builds association matrices that are actually squared matrices that have all the same size, because this is the size of the observation only. So then you can build a consensus matrix and apply OPLS on that, and you end up with a model that accounts for all the initial information that was stored within the different data blocks. And at the end, you get scores that you can interpret as you would have done with a single block data analysis. So in that case, you can see that we were able to distinguish the different extraction processes according to two dimensions. The first one was related to difference between extraction processes that extract the oil before the juice, and the other dimension was related to the processes that extract the oil simultaneously or after the juice. So the thing to understand here is that you have a score plot that you can interpret in the same way you will have done with a single data matrix. But you also have additional information that is related to the contribution of the blocks to build these new axes. And the interesting thing was that, as you can see, the first axis, the horizontal one, was mainly driven by the GC data. So mostly volatile compounds were associated with this distinction. And on the second axis, the vertical one, you can see that actually NMR, probably associated with apolar compounds, is the most contributing block. So you can see that it highlights quite nicely the complementarity you can get by combining different data blocks that will give you different pieces of information. And in that case, this was complementary information. And we can also discuss a bit the blocks associated with LCMS, positive and negative, because even if they were not that contributive to the different axes, they were also very useful in terms of interpretation for the identification of the compounds. because then we focused on a very specific extraction process, which is the sfumatrice, and our colleagues were very interested in this extraction process because it provides the best oil quality, but of course it's the most expensive, and it takes time. And of course, if they could understand what is behind in terms of biomarker, what is behind this quality, this may help them to maybe to improve their products. So by combining the loadings of the different blocks, as you can see, everything's projected in the same axis system. So then we can, looking at this, the zone where the sfumatrice samples are located, we can find variables that are specific to this kind of oil quality. And by combining data coming from GCMS, LCMS, and NMR, we were able to characterize some important compounds that were characteristic of this very specific oil quality, and then they were happy to be able to improve the quality of their products. So that's it. I'm coming to the end of my presentation. That's it for this example of multi-block data analysis. I hope now that you're convinced that there are actually solutions that are dedicated to different situations, and then that the structure of your data set is very important to apply, I would say, the right approach that will give you the better information, the best information about your data set. You can, of course, select the type of information you extract. For example, if you want to show variability, there are unsupervised approaches that will summarize the maximum of variance in your data set, data blocks, data cube. But if you want to take advantage of your experimental design to do discriminant analysis, you can also apply this kind of models to separate your groups, even if the structure is a bit more complex. And at the end, since we're using linear models, you can always go back to the contribution of the variables to interpret your models. And that's it for my part. Thank you for your attention, and I will be happy, of course, to answer your question.
Perfect, thank you. Now we're moving on to Miguel. So Miguel, you can now share your presentation.
Okay, so I think you should be seeing my screen now, right? I have to change it, okay. So
yes,
now it should be great.
Perfect.
So it's the right one. So hi everyone. So I will be continuing a bit, talking about a bit more about the third point that Julien was addressing. So it's really a data set that we acquired through multifactorial designs. And the main challenges that we are facing with this type of data. So we do acquire data which have different structures. So it can be the same samples on different analytical platforms. It can be the same samples across time. So in what we call longitudinal studies. So we will analyze the same people, for example, over time. And most of the time, these data sets have the characteristic that we have a very low number of samples compared with the number of variables that we have. And because we are dealing with systems that are influenced by so many biological factors, it's true that it has become quite common today to rely on those experimental designs to actually efficiently design our experiments, in order to have a finer look into the influence of the different factors that we suspect to have an influence on our data matrices. And for example, so Julien already talked about it, but for example, I will just, activate my pointer here. When we have a design like this, when we have the same samples analyzed over time, we can have an experimental design associated to it. And in this experimental design, we have two factors. So the first column is the factor alpha, for example, that has two levels, two different colors. it can be a group of persons, so treatment, no treatment. And we have in the second column here the time, which corresponds to 3 time points as defined by the matrices here. So we have the same design that is repeated for each of the slices. And as Julien said, not every tool can actually deal with this type of 3D data structures. So one of the ways to do it is as Julien said, is doing vertical unfolding. So we will take the time slices and we will stack them vertically. And this we can actually analyze with tools like PCA or other type of things. So because these systems that we are analyzing are so complex, it's really useful to have a tool that could help us to disentangle the information that are due to different effects, so main factors or interactions. And ANOVA is a tool that can help us with that. The problem with ANOVA is that, well, it's univariate in nature, and it cannot really evaluate the relationship between the variables. But we do know one method that is able to do that, and it's PCA. PCA can really easily handle high-dimensional data, but we are not able to disentangle the variation that is due to multiple sources. So what we would like to do in the end is really a mix of the advantages of those 2 different approaches and combine them in a single tool that will help us to disentangle the sources of variation and then analyze our highly dimensional data sets. And this equation that you saw before is really what the ANOVA step in this type of tools does. It's really a decomposition of the initial data matrix here into the main sources of variation that are defined by here 2 factors, alpha, beta, and their interaction. And then what we do is that we will do PCA, but we will not do PCA on the initial data matrix, because in this case, we will still have the different effects that will be mixed together, but we will do PCA on each of these 3 matrices here. And by doing so, we do make sure that we are only looking at what's happening inside for the variation related to factor alpha, then for factor beta, and for the interaction. And this type of tool is very useful in metabolomics because we really have a lot of confounding factors that can generate variability inside our data. And this way we make sure that we are looking at the factors that we want to investigate. And a tool that is able to do that, to combine those 2 approaches, and probably the most widespread out here, is HASCA, which stands for ANOVA Simultaneous Components Analysis. But the SCA part, don't let it fool you, it's basically a PCA. So what we see here in these colorful matrices is just another way to show the equation that we have on the top right corner of the slide. So we have our initial data matrix that is decomposed here in different matrices. So the matrix related to the factor alpha, beta, the interaction, and we have here on the top right corner the residual matrix. So it's the remaining analytical variation that is not explained by our design. So this is the first step of HASCA, an ANOVA decomposition. And then what we do is that we do PCA on each of these 3 matrices, and we will get what we all know, the scores and loadings. So the loadings for the interpretation and the scores to evaluate the magnitude of these effects. The problem is that when we do PCA on these matrices, this is what we can get. For example, this is a score plot of a factor that has 4 levels. And because those effect matrices here, X alpha, X beta, X alpha, beta, for example, here X alpha has 2 levels. Whenever a row here is red, all the red rows are actually equal, and all the green rows are equal. It means that when you're trying to represent the scores of that, you will have superimposed plots here that will show us the between variability, so the differences between the levels of a factor, but it will not show the within variability that is extremely interesting for us too. So one way to retrieve this between variability from our initial data matrix is actually to do what we call some kind of back projection, where we will take the effect matrices, we will add the residuals matrices here, X epsilon, to them, and we will do a projection onto the loadings that were previously calculated. And by doing so, we actually get a new set of scores that and these scores, called here augmented scores, will show not only the between variability, but also the within variability. So this is how ASCA works, and it's really, really useful when we are dealing with balanced designs. So what is a balanced design? So the sentence below says that a balanced design has an equal number of observations for each unique combination of levels. But what are those unique combinations of levels? To take the design here defined by YB, we have two columns, so two factors, and the first one has 2 levels, the second one has 3 levels. All the unique combinations of levels between these 2 factors, there's a total, of 6 unique combinations. And a balanced design means that we have exactly the same number of observations for each of those unique combinations of levels. And why this is important? Because a balanced design means that when we are doing ANOVA decomposition here, we make sure that our effect matrices, alpha, beta, and alpha, beta, are actually orthogonal. And this orthogonality is very important because it's the only way to make sure that X alpha is actually only explaining something that is related to your factor alpha. Same thing for the factor for the X beta. We are only explaining something that is related to beta and not related to alpha or the interaction alpha beta. And this is why it's so important to have balanced designs. But of course, as you probably know, it's very common situation to handle with unbalanced design. So it means that for each of the unique combination of levels in our factors, we don't have the same number of samples. And we have this situation where when we are actually doing ANOVA decomposition into the main sources of variation, those effect matrices are not orthogonal anymore. So what it means in practice is that it's possible that your X alpha here is actually also explaining something, some variation that is related either to beta or to the interaction. And this is something that we actually need to tackle, and we've been working a bit on that. And the problem of these unbalanced designs of experiments is on 2 levels. So I didn't talk about the bias estimation, bias effect estimators, but what it means is that sometimes in our designs, we have interactions that are not significant. So they are not really carrying relevant information. But unbalanced designs can make it look like some interactions are significant when they are not. And I already talked about the problem of orthogonality. And in literature, more recently, there's been some development. So mostly these 2 approaches. So it's a combination of the ASCA with the general linear models methodology. I will not go into details, but there's 2 methods, ASCA plus and WeASCA, that have been proposed in literature. And the limitation with this method is that we do get unbiased effect estimators, but we don't get orthogonal matrices. And for us, it is really something that is utmost important. And we've been working on, so it's still work in progress, but we are working on that, on a method that is actually able to propose unbiased effect estimators and orthogonal matrices to make sure that when we are analyzing the effect matrix of a given effect, we are not seeing mixed effects in there. And of course, the nice property also of these tools is that when we have a balanced design, all those strategies give the same results. But differences will appear when the design starts to be unbalanced. And as I say, they handle differently this idea for orthogonality between the effect matrices. So to talk a bit about the work we've been doing recently, so the method that we propose under the name RASCA for resampled ASCA is based on the following principle. So if we have an unbalanced design here on the left, and since we know that a balanced design is a design that's for each unique combination of levels has the exact same number of observations, we can perfectly imagine that we are able to generate a subset of this matrix that is balanced, which is balanced. And this is what we do here with the X, Y, B, B standing for balance. But you will probably agree with me that there's not only one way to do it. So we could do it multiple times. So we would end up with multiple balanced matrices that we can then maybe average, and we have an average balanced design. So this looks a bit weird because it seems that we have to define the number of times that we will do this game of balancing the unbalanced design. But there's actually a unique solution to that, which is based on weighted averages. I'm not going into detail, but we don't need to define this N. We have a unique solution here for the balanced design from this unbalanced one. And what we do after that is that we actually, it's the same thing as we saw in the second slide. So we apply ASCA to this matrix, we have an ANOVA decomposition, we do PCA on the effect matrices, and we get these scores that are orthogonal because the design that the matrix that we have above is orthogonal, and we have loadings that are calculated based on orthogonal matrices, so we can use them for interpretation, and we kind of make sure that when we are interpreting the X alpha, we are actually interpreting something that is related to the factor alpha. The problem is that this game of calculating weighted averages brings us back to the situation where we get the between and not the within. But what we suggest to retrieve this within variability, so the natural variability that we have in our initial design, is that we will use the ANOVA decomposition parameters that we have calculated here in step 3A to actually do some kind of synthetic ANOVA decomposition of this matrix that will give us the effect matrices that we saw before. We will add the residuals back to those matrices, and we will calculate new scores based on the loadings that we had previously. And what is nice here is that we can actually, as before, retrieve this within variability and still keep the between variability. So that's the principle of the method that we propose. It's really trying to solve the problem of the orthogonality between the effect matrices, while still being able to give information on the within variability of the levels or combination of levels. So Julien also already talked about the types of results that we have when you are doing ANOVA decomposition, especially related to the explained variance. So it gives us a percentage of the importance of a given effect in our design. But for now, we will focus more on the scores and loadings, where the scores are related to the investigation part of the evaluation of the magnitude of the effects, and the loadings, we use them for interpretation. And what we would like to do now is to know, well, how does our method deal in comparison with the other established methods? How did they deal with unbalanced designs? And the strategy, the framework that we've built to tackle that question is that we actually start from a balanced design here on the top left, XB, and we actually unbalance it in a controlled fashion by removing a specific number of observations belonging to a specific combination of levels. So once we have our unbalanced design, we analyze that design with the 4 methods that we have at our disposal. And we also analyze the complete design, the balanced one, with ASCA. And all these methods applied will give us sets of scores and loadings that we will compare. So what we do is that we will compare the scores obtained with these 4 methods with the reference case, which will serve as a way to have a feeling about how do the methods deal comparatively with unbalanced designs. And we don't do it only once, but we do it several times. What is the criteria that we use actually to evaluate the performances of the various methods? We use the RV2, which is a metric that evaluates the relationship between pairs of matrices. And it's like a correlation metric, because the closer to one, the closer it is to one, the greater the correlation between the 2 matrices, and the closer it is to 0, the lower the correlation. So this is the framework that we use to compare the methods, and this is the metric that we use in that framework. So as an example, so for this here, we use a metabolic data set of Arabidopsis of metabolic profiles that were actually wounded mechanically And we have two phenotypes. So this is our design. We have a design with two groups, the two phenotypes, and we have a second factor, the factor beta, which is related to the time after wounding at 0, half an hour, 2, and 5 hours. Our data matrix contains 72 observations, and each of these observations is defined by 124 variables. So we use this data set because it is publicly available on the Metabolomic website. And as you will see, so also are the tools that I'm talking about today. So in case you want to give it a try, it is possible to download these data sets and the tools that we are talking about. So this is the results that we get when we are comparing the scores of the various approaches with the reference case, the balance case. So we have 3 plots related to the plant type, the time factor, and their interaction. On the y-axis on each of these plots, we have the correlation. So the closer to 1 it is, the greater the correlation of the test cases with the reference case. And on the x-axis, we have actually the number of samples that we have removed per combination of levels. So when we are at 0 here, it means that we didn't remove any samples. So we are still with a balanced design. And as you can see, we have a correlation of 1 for all the methods. So we do expect that because we didn't change anything. So we get the same results for all effects. But you see that with an increasing number of observations that are removed, we have some differences that start to appear. But it's nice to see that the method that we propose here tends to have consistently high correlation with the reference case. So this is for the scores. And we have a similar situation for the loadings too. In order to give a bit more intuition into what it can represent, so this type of what an unbalanced design can actually, what type of effect it can actually have, I will focus now on the time factor, but because as you can see on the y-axis, it's the one where we expect to see the greater differences. And when focusing on this one, we have a look at the score plots. So on the top left corner, we have the reference case. So this is what it should look like. So we have a separation between all our levels of the time factor. On the bottom part on the right, as we expect in relation to the RV, the correlation values that we got, we see that RASCA has a very similar projection of those samples in this space. But when we look at the other methods, we can see that we do have a difference between the time point 0 and the rest, but we have an overlay of the different levels, and we cannot separate them completely. And this may cause a problem also for interpretation, because our samples associated to different levels are not occupying a distinct space in this multivariate space. And to give just another feeling about what can be the consequences on the loading, so here what we have is the difference, just a subtraction of the loadings of the PC2 for the time factor that we get in the reference case and the alternative methods. So we can see that the similarity between the reference case and the test case is higher when these bar plots actually close to 0. And as you can see, we have the same y-axis scale for all of the methods. So we can really see that RASCA also shows us loadings that are very close to the reference balance case, which is not the case for the other methods. And this can really have an impact on the interpretation. That's why this question of the orthogonality of the effect matrices is actually important for us. And we propose here a tool that is able, we hope, to deal with that. But of course, there's still a lot of work to be done. And just to conclude with this presentation, so as we saw, whenever we have a balanced design, the results are exactly the same for all methods. But we do have differences between these methods when the design starts to be unbalanced. And in the example that I showed you, we are happy to see that RASCA showed consistently high correlation with the reference case. This seems to indicate that this resampling strategy or weighted averages strategy is actually able to efficiently estimate those the barycenters of the levels or combinations of levels. And it shows us that this idea of solving for orthogonality of the effect matrices in addition to the unbiased parameters estimation is something that we should be focusing on. Something that I didn't talk about during the presentation. So when we have our design matrix, so the Y with the column 1 for factor alpha, then factor beta on second column, if you switch those columns, so you have beta first and then alpha, what happens with ASCA plus WIASCA and the traditional ASCA based on difference of means is that you actually get different results depending on the order of the factors in your design. And this is not the case with RASCA, which in terms of robustness is something that we are happy about and something that on which we would like to emphasize. But as I said, I mean, this is very new research and there's still a lot of work to be done. And this resampling strategy can actually be adapted to other types of methods, not only ASCA. But yeah, so this still a work in progress, and we will keep working on that. And as I said during the presentation, if you are interested into using these tools or give it a try, they are available. They are implemented in MATLAB, but you can they are publicly available via Zenodo. You have the link here, or you can get in touch with us anytime, and we will be happy to share. And of course, thank you for the EMN to have us here with you today, and thank you to Julien and the rest of our collaborators for working with us on this project. And I thank all of you for your attention. And I think Julien and myself will be happy to answer any question you may have.
Great, thank you. Thank you to both once again for these excellent presentations. We're now open to any questions that you have, so please pop your questions in the questions box. We already have some questions. So the first one, I think, is for Julien. Is there another or better approach for differential analysis for untargeted metabolomics besides the principal component analysis?
So if your aim, it all depends on the aim of your analysis. If you want to display variability in your data set, principal component analysis is probably the standard tool to be applied, and you should start first with that. But then most of the time you also have different groups depending on your experimental factors. And PCA may not be useful to display differences between groups when those differences are not part of the major trends in your data sets. So in that case, you may prefer supervised approaches that are really designed to do discriminant analysis. So there is no general method that will answer all your questions, and it all depends on your research question and on your data set. And maybe the message here is that nothing's forbidden. Just give a try to the different methods, and knowing what are their characteristics, then you can try to dig a bit in more details into your data set.
Okay, thank you. So we have another question from another attendee. So first of all, she says, thanks for your very nice talk. And she was wondering about the software that you use in your lab for data analysis. If you are used to R, which kind of package are considered fundamental for the data treatment or analysis that you presented?
Thank you. That's true. That's a very good question. Actually, we use different softwares depending on the aim of our project. I would say that for standard multivariate models, I think of PCA, PLS, OPLS, we have commercial software that will, and so that many of our colleagues can also use this solution. And this is very easy to handle, to import your data. And this is very efficient to get nice models that are well validated quite quickly, and with plots that you can start to interpret. But it is only valid for, I would say, classical methods. All our developments are done in MATLAB, just because this chemometrics is more related to, at the very beginning at least, to chemistry, and chemists really like to work with MATLAB. I fully know that today bioinformatics and biostats are mostly associated with R. So of course you will find most of the tools that are also translated into R. I also need to mention Python, of course, that can be very efficient to implement existing methods. But I would say that it may be useful if you want to use these kind of things in a more large scale, I would say, rather than developing a new algorithm. In my opinion, in our opinion, platforms such as R or MATLAB may be the best solution to develop things. And then you can translate the tools in Python, for example, if you want to be more efficient.
Perfect. Thanks for your answer. That's the next one is for Miguel. Can we use these models for 3 groups? Balanced number of observations design with the 6 observation time point.
So thank you for the question. I believe that there's no limitation with respect to the number of time points or the number of groups that you may have. For example, I worked with longitudinal data in nutrition where we had 14 time points and we had people, so it was a total maybe of more than 10 people. So there's no limitation with respect to that.
Okay, perfect. So there's another question. What do you recommend to normalize data when you have a time-dependent dimension? Is there a risk to smooth the time dimension during the normalization?
That's actually not an easy question, because it's, I think in most of chemometrics and metabolomic studies, normalization of the data or scaling of the data still remains some kind of bottleneck, because there's no gold standard. So a way you should do this way and not the other one. So I don't know if Julien has maybe more more aspects to the answer than that, but I mean, it should make sense from, let's say, an intuitive point of view, and it should make sense with respect to the nature of the data. But Julien, maybe you can add something to that.
Thank you, Miguel. You're right. It's a tough question, actually, and it really depends on the application and the kind of sample you're dealing with. I would say that there are different normalization steps that can be applied. First, there is a pre-analytical normalization step that can be applied, for example, to urine samples, where you will try to dilute slightly your samples so that they are analyzed at the same level in your analytical device to flatten potential differences before the analysis. Then you can apply normalization strategies after data acquisition. You probably have heard about probability quotient normalization, for example, things like that. This is done on the basis of the data you collected, but you can also correct for differences in concentration based on another external parameter that can be associated with the number of cells, the amount of protein. I don't know. There are many different ways to normalize the samples even after data acquisition. And regarding more specifically, maybe your question regarding the time points, some approaches are designed to compare all the different time points to the initial situation, to the T0. And again, for some research questions, it could be a good way to proceed. And then you will have ratios of metabolites intensities or abundances compared with the initial situation. And this can also be quite efficient to normalize your signals.
Great, thanks both. The next question is about the multi-block approach, which starts by building a consensus matrix from different input matrices. So how is this consensus calculated?
So the very naive way would be to superimpose all the different matrices. And if you do that, it means that you allocate a weight of 1 to each of the data blocks. Actually, the solution is exactly the same as you would have obtained with the PLS, for example, with concatenate data matrices. So it's not really an improvement to do that, but just to let you know that you can get the solution you would have obtained with concatenation of the data matrices. Then it can be very interesting to play with these weights to give more importance to blocks that are more predictive of the response. And that's actually what we do with this consensus OPLS approach. Again, we use the coefficient Miguel described with this RV coefficient to assess the correlation between each of the data blocks and the response metrics. And this can be used to allocate more weight to the most predictive blocks. And in that case, you get a model at the end that is more predictive than the one you would have obtained by only concatenating the data blocks. But again, this is one solution, but there is a lot to improve. You have to be creative, maybe, to find new solutions that will give another viewpoint on your data collection of data matrices.
Great, thanks a lot. There is another bioinformatics question for Julien. So could you guide us on how to choose the number of permutation tests in an unsupervised PLSDA validation?
So PLSDA is supervised, and you're right, it's very important to validate the model. It's also very useful to evaluate the right number of latent variable of components of your PLSDA model. So on the one hand, you have a cross-validation that is helpful to do that. And you mentioned permutations. And permutations is also very efficient when you mix the response vector. And what you expect to see is that your true model is much more predictive than models obtained with permuted response. And in that case, well, I would say, as usual, the larger number of permutation is the best. If your computer is quick enough, let's say that 1,000 could be nice. But again, it's also depend on the number of observations. But because at some point, if you have a very small number of observations, the permutation will not allow you to draw an unlimited number of solutions. So if your number of observation is small, it's probably not useful to go to this kind of value.
Perfect, thank you. So the next one is for Miguel. How does your model compare to other models that include mixed models such as LIM-PCA and RMASCA?
So the methods I present today are really limited to what we call fixed effect factors. And for example, the time point could be considered as a random factor, but here we consider it as a fixed effect factor. It's quite common to do it this way when we are actually in an explorative process. So we are not really doing predictions, but we want to see, well, what is the difference between the levels of our factors, interaction, etc. So it works well in that aspect, but for sure there's been recently developments with the mixed models, which are very interesting, and I believe this is really the way to go for the future developments in this field, or with respect to the question of dealing with the multifactorial designs. And this is actually something that we would like to dive a bit further into. But yeah, so I've not compared these approaches directly with methods like LIM-PCA, or there's another one like repeated measures ASCAPus that was published more recently. But this is something that is on the agenda and that we would like to work on in the near future.
Thanks. So there is another question. So what do you think about working with deltas, for example, to reduce one dimension such as time or effect?
So maybe can I have more information on what deltas mean? Or maybe did you understand, Julien?
I don't know if I get it right, but maybe if you start to compute differences, these deltas between a reference situation and another, I don't know, time point, or?
Yes, exactly. That's what they mean. It's T2 minus T1.
Yes, you can do that, but then it can be difficult to really assess what happened between the two time points, because you at the end you will get a single data matrix. I know that there was a method that was based on OPLS and the subtraction of before and after situation, but then you use the OPLS model in a weird manner, because you have to, if I remember well, you have to predict a constant vector to see what changed between your two situations. So that's true that you can compute, you can subtract the different situations, but then it's not that easy to interpret the resulting matrix, to my knowledge at least.
And if I can add something, I mean, I would say it also depends maybe on the question that you're asking, but what I found very interesting about methods like ASCA and derivatives is that when we are working with a time factor, they are actually able to spot nonlinear trends in time, such as circadian rhythm or the consumption of after a challenge in nutrition science. So it really depends on the question that you're asking. And maybe when you work with differences, maybe you don't have the overall picture. But once again, I mean, as always, it's not the answer that we would like to hear, but it depends on many things.
Perfect. Thank you both. I think that was the last question that we had. Again, we would like to thank both of you for the great talks and the great answers to all the questions. And we would also like to thank the attendees for joining